A recurring function, as I like to call it, is an expression which uses another occurrence of itself to calculate the current step. Okay, I'm bad at explaining things in a short manner, which is why this is a long form video. So let's get into what a recurring function is. This kind of has to do with self-similar fractals. If you don't know what that is, it's a shape with infinite detail that is made by repeating some kind of alteration to a shape, like a line that then extends into infinite lines, which then get gradually smaller with each iteration. A super popular one is called the Sierpinski triangle. In a Sierpinski triangle, you start with a triangle. Yay! Subdivide into 4 congruent triangles and remove the center one. Then you keep doing that with the smaller triangles infinitely. You get this really cool and infinite detailed triangle. The reason we call this a self-similar fractal is because if you look inside, you can just keep finding more of it. A Sierpinski triangle is composed of infinite copies of itself. Now, how does this relate to recurring functions? Well, recurring functions are a lot like self-similar fractals. A recurring function uses itself to then apply changes. Let's just get an example here. F sub n equals f sub n minus 1 plus 1. Basically, this expression is saying take the previous number in this list, increment it by 1, and then return that as the value of this index. So, say you start with f sub 0 being 0, then it'll go 1, 2, 3, 4, 5, and so on. That's cool. Okay, so now that you've learned a bit, here's your question for homework. What's f sub 2 if f sub 0 is 2, and f sub 1 is 4, where f sub n equals f sub n minus 1 times f sub n minus 2? Make sure to pause the video before I reveal the answer. The answer is f sub 2 is 8. This is because the rule says take the last 2 numbers in the list, multiply them, and return that as the value of this index. And we defined the base indexes as 2 and 4. And 4 times 2 is 8. Here's one example of a recurring function, the Fibonacci sequence. Everyone knows this, right? The rule for this is f sub n equals f sub n minus 1 plus f sub n minus 2. Pretty simple, but it's used everywhere. For example, some softwares have Fibonacci numbers as their zoom level presets. The reason for that is because it grows exponentially, but doesn't get super big super fast. And that nice organic growth is pretty to the eyes. A fun fact about recurring functions is you always need base cases based on how far the recurrence goes. If a rule refers to an index 6 indices away, you need 6 base numbers in the set that go before the first applied index. For the Fibonacci set, you need 2. For my first example, you need 1. Though, normally you don't even need to define these base cases yourself, as famous sequences like the Fibonacci already have a standard base case. For my first example, I'd say the standard should be 0 or 1. Those standards aren't set in stone, obviously. You do whatever you want in math, it's all made up anyway. One recurring function I came up with relies on 2 variables, m and k. The rule is f sub n equals f sub n minus m plus k. So m is how much you go back, and k is how much you add. My idea when writing this was to find a set of k and m that didn't have 1 as m and didn't repeat numbers. For example, if you set f sub 0 and f sub 1 to 0, k to 2, and m to 2, you get 0, 0, 2, 2, 4, 4, 6, 6, etc. This doesn't achieve the goal. Sad. Anyways, I don't know what else to say, and I have no idea how to exit this video, so bye, hope you learned something or enjoyed my rambling! Cut?